Physics 2212, Lab 2, by Christian Medina. Introduction and reasons for our data. The reasons for our experiment are to charge two pieces of tape, determine the interactions of charged objects with other objects, determine the amount of excess charge on the tape, and use a simulation of PHYS to show the electric field interaction, and to calculate the amount of total charge. The data that we collected was the charged tape had a net positive charge. Charge on the tape is 14.9 nanocoulombs, and the tape is efficient 9.28 times 10 to the electrons. Introduction and important equations are Newton's second law. Net force on an object equals its mass times acceleration, and this relates the net force of the object to the mass and the acceleration of the object. The force of gravity near Earth's surface is Fg equals mg, which acts in the y direction, and g is the constant of 9.8 meters per second squared. The electric force is the force of two charges and the distance squared between them times a constant k. Fe equals Coulomb's constant, which is 9 times e to the 9th, times two charges, times your magnitude of r squared times r hat, which gives you your force as a vector, or if you just multiply by the absolute value or your magnitude of r squared, you get your absolute value of force, or your magnitude of force. The assumptions we made is that the charge on the tape is evenly distributed along the tape. Both tapes have the same amount of charge, air resistance is ignored, and the density of the tape is constant throughout and is only one atom layer thick. The procedure to make this is you create two U-tapes by placing one tape on top of a table and taping another strip of tape on top. You pull off the U-tape from the base tape. Repeat steps 1 through 2 to make two U-tapes. Observe the interaction to the U-tape and a neutral object. Observe the interaction to the U-tape and a charged object, like a plastic pen rubbed on hair. Suspend one of the U-tapes on objects of equal heights. Place the other U-tape below the suspended U-tapes and observe the separation distance between the two tapes. Observation that we made was that the U-tape and the neutral object attract. Interaction to the U-tape and the pen attract because the pen is negatively charged with the abrasion against hair, moving electrons from the hair to the pen. This means that the U-tape is positively charged as they experience an attractive force. Interaction with two U-tapes, they repelled, and when suspended, they experienced a separation distance of 1 centimeter. The free body diagram here, the system is suspended U-tape, the red rectangle. The surroundings are your held U-tape, the blue rectangle, and the Earth. 1 is the electric force from the held U-tape on the suspended U-tape. 2 is the force of gravity. 3 is the holding force from the hands on the held U-tape. And 4 is the electric force from the suspended U-tape on the held U-tape. At equilibrium, the net force in the suspended U-tape is 0. Experimental data calculations. Our tape length was 0.2 meters. Tape width was 0.02 meters. Tape surface area is 0.004 meters squared. Number of atoms we got was 4 times 10 to the 17, which we got by dividing your surface area by the area of an atom, which gave us the number of atoms. Vertical distance between the two tapes is 0.01 meters or 1 centimeter. The tape weight was 0.00196 newtons, which we got by multiplying the mass, which we got by multiplying your length times your linear density, and then we multiply this by 9.8 to get your force of gravity. The force of gravity on the U-tape is only acting in the y direction, so that's why it's in the vector in the y direction. The charge on the U-tape was 1.49 times 10 to the negative 8, or 14.9 nanocoulombs. We got this by setting your force of gravity equal to your electric force, which our electric force was equal to the radius away from the tapes times your length divided by 2, half your length. We got this by taking the integral of your linear density and setting that equal to your gravitational force. So you end up getting this big equation, which you can acquire by taking the integral of a small amount of dq over a small amount of length, dl, multiplying that by your linear density to get your q at a certain location. It is deficient 9.28 times 10 to the 10 electrons, and the ratio is 1 electron for every 4.31 times 10 to the 6 atoms. Your VPython simulation here shows the electric force in green, your downward gravitational force, and then the other force is hidden up here, but it's your electric force pushing away. This is the VPython code. The discussion: the U-tape is positively charged with missing electrons. In order to float, the force of gravity and electric force must be equal. Possible sources of error may be inaccurate measurements inaccurate measurement of separation distance, and may not have been held parallel. 1 was modeled as a point charge with 4.6 nanocoulombs, while Lab 2 had an estimated charge of 14.9 nanocoulombs. The charge in Lab 2 is about 3.19 times greater than Lab 1. Differ in Lab 1 because in Lab 1 they're treated as point charges, while in Lab 2 they're treated as charge spread along the length of the tape. The Lab 2 value is much closer to the actual charge because charge likes to stay far apart because they repel, which means that it would spread over the length of the tape.